Hi guys, here we are again. Looking at today, we're going to be dealing with surface area and volume of a cone. So we've got this, and then one more little bit tomorrow, Friday, that we'll be dealing with surface area and volume of a sphere. So think like a basketball or a baseball. So a cone, just like an ice cream cone. And then that'll be the end of this chapter. So this chapter next week we'll be doing some review, and then kind of doing an assessment-ish way of doing this, so that you can kind of see, wrap everything up and make sure that we kind of have a basic understanding of all of the different topics. So this is a big chapter, and we'll see how we go, how we do from there. So let's go ahead and start. We're going to start just with reviewing some of the ideas of pyramids, and then incorporate that into how it works with cones as well. So let's go ahead and get started. So here it says, review what you learned in the last lesson by finding the volume of each pyramid below. So remember that our volume formula for a pyramid, we said, was going to be, maybe if I can get this thing to write, there we go. Our volume formula for a pyramid was going to be the base area times the height divided by 3, because it took 3 pyramids to fit into one cube. So really all we need to know here is what's the area of the base. So in this case, our base is a rectangle. So our base area would just be, come here, you. Okay, let's try that again. Would just be 14 times 6, because that's how we find the area of a rectangle. So that's going to give us a base area of 84. And the height of the pyramid, we can see straight up and down height is going to be our perpendicular distance. So our height in this case is 19. Oof, my handwriting's getting really bad here. Let's try that one more time. Height equals 19. Okay, so then what we're going to do is we're going to plug this into our volume formula. So volume is going to be the base area times the height divided by 3. So that's nothing too terrible there, I hope. That's going to give us a nice easy volume. Just calculating it, typing it in the calculator, and I get 532. So units cubed, because it's the volume. Nice save there. This one is even easier, because even though we do have a hexagonal pyramid, it's a right pyramid, we can see here, straight up and down the height would be the same as the height on the outside. They gave us the base area already, so that works out really nicely. So we know our height then has to be the 36. So to find our volume, we're going to just type this into our calculator, 259.8 times 36 divided by 3. So nothing too bad there. Type it in. We're going to get some really big numbers here, because our volume is, our area and heights are so much higher. So we're going to get 3,117.6 units cubed for the volume on that one. And then one more here, we've got a right triangle for the base. So the base area would be the area of the triangle, which would be 4 times 9 divided by 2. So 4 times 9 is 36, and divided by 2 gives us a base area of 18. The height of this pyramid is 13. So then our volume will be 18 times 13 divided by 3, which gives us a volume. If we type that into the calculator, we're going to get a nice easy number of 78 units cubed. And we can see, like, looking at these numbers, our values, especially for our base, were so much smaller on part C, and our base was so much smaller. It's only a triangle, whereas here we had a hexagon, here we had a rectangle. So our values were smaller, and the base has a smaller area, which is why our answer is so much smaller. And also our height was smaller in all of compared to the other two. So that's why that works out like that. So now that we feel like hopefully we have a pretty good example or groundwork for volume of pyramids, how does that affect the volume of a cone? So while finding the volume of the pyramids above, Jamal asked, what if it's a cone? How do you find its volume? Notice a cone is a three-dimensional figure that consists of a circular face called the base. So here we have our base, and a three-dimensional figure, a point called the apex that is above the base, and the lateral surface is kind of going to contain this area around. It kind of makes this triangular shape. Think of it like an ice cream cone, or like a cone-shaped cup, you know, that paper cup that you're thinking of that the water would go into, that's kind of what we were dealing with there. So if we were thinking about how to find the volume of a cone, kind of trying to take a guess as to how this would relate to pyramids, hopefully this YouTube video will come up. Let's see here. Maybe it's thinking. We're not going to watch all of the video either, so apparently my internet's working a little slow right now. Just kind of taking a guess as to how pyramids and cones might be related. They both have a singular base. They both have a point above the base, and they both have triangular values, triangular areas towards the middle. So here we have our cone, and we are going to, let's see here, we are going to skip ahead a little bit because we've already discussed this. There we have a cylinder that is the same base area, has the same circle and the same height. We can see that. Let's see here. Trying to skip ahead so that we don't have, oh, there we go, same base area. And we can see here they have the same height. Observe what happens next. So if we were to, my other computer just freaked out on me. If we were to take our cone with the same base area and the same height as the cylinder, I don't know who that is, and fill it up with water, we can a cone that is completely filled with water. They are very thorough in their video demonstration here. We can see that if we fill this up one time, this cylinder with a cone, that we have not quite halfway. It looks like maybe even a fourth of the way up, but maybe not. So now if we fill a second time, we can see that we've exceeded half. So it didn't go only a quarter of the way up, it must have gone about a third of the way up. And so now he's run out of water in the bucket there, but he's trying to, without dropping anything, fill that pyramid or that cylinder all the way up. And so we can see there that if he fills it, it gives 3 cones to fill up one cylinder. And so then, just like we saw with the pyramid, that it takes 3 cones to fill a cylinder. So how does that work with our formula then? Well, we knew that a cylinder had a volume that was pi r squared, the area of the base, times the height. So if it takes 3 cones, then we're going to use the same idea, pi r squared times the height, and then we'll just divide by 3. And so then here's what we'll do. Here we have in our picture, we have a cone. The entire width of the base is 16 millimeters wide, which means that the radius of the base would have to be half of that. So our radius would be 8 millimeters. So if we know that the radius is 8 millimeters, and the height of this cone we can see very clearly is 12, then we would multiply and divide. So we can plug our values in. 8 squared would be 64 times 12. We've got our pi out front there, divided by 3. So I'm going to just leave this in terms of pi. And so 64 times 12 is going to give me, let's see here, I wrote this down, 768. So I have pi times 768, and I'm going to divide that by 3. And that will give me a nice answer of 256 pi millimeters cubed. So volume of a cone is almost the same as the volume of a pyramid. You're still going to multiply the area of the base times the height, and you're still going to divide by 3 because it takes 3 cones to fill one cylinder with the same base area and the same height. So hopefully that helps out a little bit there. We'll come back in just a second to discuss surface area of a cone and how that might be related, possibly, to the formula for a pyramid and a cylinder and how those kind of all relate to each other. So come back and I'll talk about that, and we'll do some examples over all of those together.